Hello and welcome to this presentation on semantic information systems. I will illustrate how to leverage semantic modeling to enhance the efficiency of any information system. The concept involves integrating semantics with knowledge graph databases on LLM AI technology. My name is Pierre Bonnet. I am an expert in enterprise architecture and data management. I am a French citizen located in Paris, France and Vietnam. I've authored several books in my domain of expertise, as you can see on this slide. You can find my books on Amazon. Beyond this presentation, you can visit the website of the Engage Meta community to find out more information. We propose best practices to create a bridge between digitalization transformation, data management, artificial intelligence, and knowledge management. All these disciplines are unified thanks to the enterprise architecture approach. We believe this is the right way to reach success with digitalization transformation impact. First, let's take a closer look at semantic modeling. The primary objective is to clarify the business concepts used by a company to operate, irrespective of its organizational processes. Each business concept should be precisely defined within a glossary. To structure this knowledge, it's often beneficial to establish a hierarchy of these business concepts known as a taxonomy. This taxonomy aids in distinguishing and clarifying both general and specialized business concepts. Without a well-defined taxonomy that has received approval from all stakeholders within your organization, you will find yourself missing a crucial element for progressing with AI. You will gain a deeper understanding of these as we proceed through the rest of this presentation. To enhance the glossary, a list of synonyms is compiled, which in turn contributes to the creation of a thesaurus. Therefore, at this stage, you require a glossary, thesaurus, and taxonomy. Now it's time to delve into the actual modeling of semantics that exists among the business concepts. It involves creating a robust data model that defines the relationships between these concepts. It goes beyond a simple hierarchy and forms a network of relations known as an ontology. In some instances, certain segments of this taxonomy can be represented as relationships. For example, you can see that the roles client and partner are reused for the business concepts individuals, corporate, and partner. Within the ontology, you will observe that this implementation is represented as a qualifying attribute, a role, featuring a recursive relationship called played between two instances of the person business concept. Feel free to pause the video and take a moment to appreciate how the ontology restructures and enriches the taxonomy to create a comprehensive semantic data model. This data model will later be utilized to populate a graph database engine and manage data values effectively for AI purposes. While the ontology serves as the static component and is considered typically the final output of semantic modeling, it will be a huge oversight to focus solely on this static description. Each business concept undergoes a business lifecycle that delineates its various states and transitions over time. For example, look at the person business concept and its state machine illustrated on this slide. You will notice that a person starts in the prepare state, progressing to create state once the preparation is complete. Only after the check level 1 operation is conducted does it transition to the validate internally state. With a precise depiction of the business state values for a given concept, you can significantly enhance the security and reliability of your system. For example, if a process wants to run a business operation with a person instance whose state is not compliant with regulation, it will trigger an alert. This allows the business concept to safeguard itself by ensuring that no entity, whether a process or a human, violates its state machine. As you delve into the use of artificial intelligence, you will discover that effectively managing these state machines plays a crucial role in controlling AI errors. I would like to clarify the distinction between the state machine and the workflow. As illustrated in this slide, a transition between two state values occurs through an operation, such as check level 2 in this example. This operation may encompass the execution of a workflow within the organization involving different actors, as seen here. The crucial point to grasp is that the state machine remains entirely unaffected by organizational changes. Even if the organization undergoes a complete overhaul of the workflow for executing check level 2 operation, it will have no impact on the state machine. This clear separation between the core business, represented by the state machine, and the organizational workflows is fundamental. It not only enhances the security and reliability of the system, but also augments its agility. This means you can adapt the organization, potentially leveraging AI, without risking the integrity of the core system governing the life cycles of your business concept. The final aspect to consider in semantic modeling is the creation of identifiers for business concept. These identifiers serve two primary purposes. Firstly, in real-life scenarios where a business concept instance needs to be identified independently of any software, such as a client identifier on a paper format invoice or for communication with a call center. Secondly, these identifiers are used to establish the primary business keys in databases. The definition of business identifiers should adhere to a naming convention to ensure consistency in human reading rules. This practice helps ensure the ontology is well designed. Ultimately, the goal is to achieve a seamless alignment between the semantic data model and the structure of identifiers. In summary, semantic modeling is a stack composed of these layers: glossary, thesaurus, taxonomy, ontology, state machine, and business identifier. Naturally, it's impossible to design your organization's entire semantic management stack all at once. Instead, this process should be approached progressively. The importance of this semantic management stack becomes evident as we delve into the enhancement of LLM AI, as I will explain later in this presentation. But for now, let's explore how we can implement the semantic. In this part of my presentation, I want to highlight three different technologies for managing data. The most common one is OLTP, which stands for Online Transactional Processing. It's highly efficient for handling large structured data sets in a transactional mode, primarily focused on update processing. The most popular OLTP solution is the relational database. Next, we have the knowledge graph database, which organizes data in the form of sets of triples. In this structure, one node is linked to another through a relation. It's user-friendly and does not require complex IT processes to implement. However, it's often best suited for read-only use cases or scenarios with limited simultaneous updates by multiple users. Let me explain a bit more. A knowledge graph database is based on a triple approach for data storage. The concept is relatively straightforward, involving the manipulation of nodes on edge through triple exclusively. As demonstrated on this slide, this approach applies to both the data structure and the data instances views. The capability to present instances in this manner is advantageous when compared to conventional relational databases, which typically have more complex user representation than a simple graph. The process of mapping data from a relational structure to a node-based structure is not straightforward. There are various methods for mapping the two approaches, and you must decide how you intend to use the knowledge graph. You have flexibility in how you utilize triples to suit your needs. In this slide, you can see that all tables and attributes have been transformed into multiple nodes and edges. This can make it somewhat challenging to identify the business identifier, namely the primary key, and the model becomes more permissive. To address this, I've chosen to emphasize the business identifier by using a naming convention for the age, specifically the is a member relation. While this may make the graph appear somewhat more complex than a relational tables data model, knowledge graph databases typically offer also a more streamlined view with one node per table and direct attachment of attributes to these nodes, as seen on the right side of this slide. This provides greater clarity. Additionally, it's important to note that this representation of nodes and edges also applies to data instances offering significant advantages for user queries on AI prompts, which I will elaborate on later in my presentation. Let's summarize the differences between the typical relational database tables and the knowledge graph database. The primary advantage of a knowledge database lies in its flexibility in representing relationships between business concepts. It eliminates the need to manage foreign keys, which is particularly advantageous when dealing with data instances. However, there are potential risks in terms of data integrity when using a knowledge graph for transactional data updates. In such cases, it may be more appropriate to stick with a traditional relational database, possibly adopting a NoSQL or NoSchema approach to ensure flexibility in managing data structures. In today's technological landscape, it's essential to find a way to integrate these two technologies, depending on the specific use cases a company aims to implement. I will now revisit the slide that highlights the comparison between the three technologies. Lastly, we have a new approach, which is not exactly a database engine, but rather the neural network of an LLM AI engine to store data. Here, data is transformed into parameters within the LLM engine, primarily for text management. I recommend pausing the video to review the different features I've presented here. You will see how they vary depending on these three database technologies. Unfortunately, the current state of IT doesn't offer an all-inclusive technology that covers every aspect. Therefore, an information system architecture must rely on these different approaches to create a comprehensive solution. I will revisit this holistic approach later in the presentation. If you are unfamiliar with concepts like operational data store or master data management, feel free to check out my other videos or reach out via email with your questions. I will be happy to assist you. Now I would like to share my vision of what I refer to as holistic semantic prompting, which essentially combines the power of LLM like ChatGPT with knowledge graph. Here you can see a user prompt that references various business concepts and requires real-time data retrieval from the information system. Let me read this prompt for you. Provide me with the customers who are most likely to make additional purchases based on our current warehouse stock information from the last hour and who are located within 100 kilometers of their delivery addresses. This prompt is interpreted by a query composer which extracts formal concept, business concept in red, time-related concept in green, and geography-related concept in blue, such as addresses and locations. The composer utilizes this concept to query additional databases that have not been integrated into the LLM's training data during the AI preparation step. These additional databases include semantic data from the knowledge graph database and real-time transactional data required to enhance the prompt and improve the LLM's analysis. Training LLMs with large datasets is a resource-intensive process, so it's essential to exclude transactional data from these datasets. Instead, this dynamic data is injected in real time through the RAG API or Retrieval Augmented Generation API. In summary, the query composer enriches the initial user prompt with information related to business concept, time, geography, and real-time data if necessary. This allows the LLM to work with more refined data, resulting in smarter and more comprehensive responses to the user. Another key advantage of the query composer is the ability to check the quality of the LLM response. As you can see on this slide, the LLM-generated text includes some formal references to the business concept in red, the time management in green, and the geography in blue. Therefore, the composer can easily fetch the databases to check if the response is reliable against the actual data within the information system. It allows for the detection of potential hallucinations and help the user have a better interpretation of the LLM answer. Of course, for business-oriented user prompts, it's not possible to let hallucinations go without any compensation processes. The query composer, by relying on semantic management, is a good solution to balance LLM and reliability factors. Finally, we can confirm that LLM plus knowledge graph leads to holistic prompting. Now it's time for my presentation to show you the big pictures through a blueprint for a semantic information system. First, I need to recap some key definitions that will help you navigate through the blueprint I will present on the next slide. So let's review the definitions together. Semantic modeling. Modeling business concept with glossary, thesaurus, taxonomy, and ontology. Semantic engineering, using a knowledge graph database to implement the semantic models for validation and test with business users. Running with AI, operating the information system with quality data on AI. AI learning and governing, managing AI learning, creating intelligent algorithms and governing AI. Supervision with AI, intelligently monitoring information system execution using AI to detect errors and opportunities. Operational data store, operational data repository that unifies all data across silos using a semantic model. Implementation can occur in either write mode, OLTP, or read-only mode, knowledge graph. MDM for data flows and enterprise. Reference and master data repository, which makes it possible to unify exchanges at the ETL EAI level and to disseminate shared data throughout the information system. Knowledge data store. Knowledge repository which contains part or all the ODS data to have semantic management and contains the stock of unstructured information necessary for artificial intelligence, contents on or links to a CMS. Let's start with the blue cycle in the middle. This illustrates the semantic modeling with the 6 components I've already described at the beginning of this presentation: glossary, thesaurus, taxonomy, ontology, state machines, and business identifier. This material is integrated into a knowledge graph database, as you can see on the right side of this figure. I refer to it as the semantic engineering repository because it also aids in the construction of semantic modeling by providing a clear, user-friendly UI for data models and data instances validation through graph representations. With the power of the LLM engine, it's also possible to automatically generate initial versions of these semantic components by extracting legacy knowledge from data structures, user guides, specifications, etc. However, constructing the semantic material is not a one-time process and requires continuous refinement. This is an ongoing task as the core systems, silos, and other software packages change over time. Now we add the 3 key data repositories to run the system. The MDM for data flows and enterprise data, responsible for the reference and master data that are shared across the entire information system. Then the operational data store that contains transactional data, either in write mode with an OLTP database or read-only mode with a knowledge graph database. In this example, we are considering the use of a knowledge graph database. Finally, the knowledge data store, or KDS, which contains all the semantic material generated during the modeling process. It is also used to collect individual and collective knowledge, namely unstructured data such as text, voice, and video, which is linked to the ontology to accumulate knowledge in a unified manner. Now let's explore the integration of the query composer I've described earlier in this presentation. As you can see, it is connected to the RAG database, which exposes transactional data from the operational data store, and the knowledge data store to retrieve the business concept required to enrich user prompts and check for hallucinations, as I explained in a previous slide. Please note that the large and stable datasets used to train the LLM are regularly updated with the stable part of the knowledge accumulated in the KDS repository. Fortunately, I cannot show all the connections in a single figure. Now let's integrate the AI governance platform used by data analysts and AI experts to train machines learning on structured and unstructured data to develop intelligent algorithms. This governance platform leverages the semantic knowledge stored in the KDS repository. For instance, when dealing with a business concept like client, the KDS provides all the relevant logical dataset references that AI experts can utilize to create their intelligent algorithms. In other words, the AI governance operates at the semantic layer rather than the logical layer, ensuring a more robust and smart governance that mitigates the risk associated with improper handling of logical data. It's important to note that additional security and confidentiality layers must also be implemented to safeguard data values and ensure compliance with confidentiality and regulatory policies. Finally, we incorporate the AI-powered governance, a concept I've discussed in previous videos. These involve implementing an AI system that continuously monitors the specifications on real-time data within the information system. This AI is designed to raise alerts in case of unusual software execution or data utilization patterns. Additionally, it can provide recommendations for various improvements that may be challenging for a human to identify. This AI operates by comparing expected behavior against the actual executions of the information system. As you incorporate more intelligent algorithms based on AI into your applications, the risk of system malfunction increases. It's crucial to proactively mitigate this risk by preventing incorrect automated decisions and promptly identifying and addressing issues when they occur. In conclusion, you now have a comprehensive blueprint for what I refer to as the semantic information system. I encourage you to pause the video briefly to review it once more, as it encompasses many innovative concepts. You can clearly see how semantic modeling serves as the central cornerstone of this entire architecture. Here are the 3 takeaways of my presentation. Firstly, it's crucial to remember that without a robust semantic modeling strategy, integrating AI at a large scale into your information system becomes a challenging endeavor. As you increase your AI implementation, you must also elevate the level of semantic control within your information system, essentially formalizing its intelligence. Secondly, it's essential to provide users with a solution for accumulating both individual and collective knowledge. This knowledge accumulation is pivotal in enhancing the capabilities of your AI systems. Lastly, AI governance should be applied at the semantic layer of your information system, and it should be reinforced by an independent AI-powered governance system. This dual approach ensures that you maintain control over the decision-making processes driven by AI's intelligent algorithms. These takeaways underscore the importance of holistic semantic management and governance in successfully integrating AI into your information system. This concludes my presentation. Please don't hesitate to share your thoughts in the YouTube comment section below the video. We'll be happy to read and reply. You can also watch other videos on our YouTube channel. If you would like a copy of this slide deck, don't hesitate to send me an email. Additionally, if you have any questions or would like to explore this topic further, I will be delighted to provide more information. Thank you again for your attention and see you soon. Bye-bye.